taking you behind the scenes of the National Institute for Data Science and Artificial Intelligence.
With unprecedented access to the scientists pushing boundaries and shaping our future, this show will take you to the cutting edge and beyond.
And whether you're an expert yourself or just science curious, this is the show for you.
Welcome to the Turing Podcast.
Hello everyone and welcome to the Turing Podcast. I'm your host Ed and I'm here with B. Hi B.
Hello.
And today we're joined by Dr. Scott Hosking, who is a co-director for the Alan Turing Institute Research and Innovation Cluster in Digital Twins, as well as the founder and leader of the British Antarctic Survey AI Lab. And we're also joined by Dr. Jonathan Smith, who is a principal research scientist also at the British Antarctic Survey AI Lab. So Scott and Johnny, welcome to the podcast.
Hey, yeah.
Hello.
Welcome. So I guess before we go to any of the more researchy questions, I guess we can start to listen a little bit about yourselves. So if you can just tell us in a few sentences about, how come you came to work at here, at the Turing or at BAS. So maybe we can start with you, Scott.
Yeah, thank you, B. So I'm a climate scientist by background. And then in around 2015, I set up the AI lab at the British Antarctic Survey. Well, we set it up formally a little later, but we started thinking about let's bring AI into our methods. And we set, there were discussions internally. So in 2018, we officially launched the AI lab. And at that point, I started meeting with leaders at the Turing, so the program directors at the Turing. And, that's how we started our formal collaboration. And then an opportunity arose where I applied to join the Turing as a secondment, and I've been there ever since 2020. So I'm now helping set up, leading the environment and sustainability grand challenge until we get someone in post. But yeah, that's my background and how I came to be at the Turing.
Well, Johnny, maybe you can tell us a bit about your background and also the British Antarctic Survey. What is it? And
Okay. So to start off, my background's actually in geophysics. So I started looking at earthquakes, specifically using machine learning methods to detect, locate, and understand the dynamics subsurface. But when I returned back to the UK after doing a postdoc at Caltech, I started to see some really interesting jobs come out of the AI lab at the British Antarctic Survey. So to answer your question on what is the British Antarctic Survey, they're looking at monitoring and understanding the Antarctic region. And this could be from ecological background, this could be from environmental background, and understanding stuff like climate change. But also the AI lab, more specifically, is looking into forecasting these conditions through stuff like IceNet, and Scott will talk about this later, and also understanding how we can reduce our carbon costs for operations. So stuff like how do we navigate our ship in these complex conditions? So since joining, I've actually taken up the role of principal research scientist, and I'm a co-leader of the Autonomous Marine Operations Planning team.
It's cool. I mean, we'll talk about the actual research, but I just have to get this question out of the way. So we do if you do field trips to the Antarctic.
Oh, no. I've been at the British Antarctic Survey for 14 years and I've not got to go yet. So yeah, you're talking to the wrong people. I can show myself out if
Members of our team were lucky enough to go on the ship this season, and we're hoping to get more on next season to look at ice navigation.
Okay, great. So it's great to hear that the computer scientists and the AI people are not excluded from fieldwork entirely.
I guess the main thing that we wanted to have you here today is to talk a little bit about the research that is coming to be to make a digital twin of Antarctica, right? So I guess first, before any specifics, can you just briefly remind our listeners what is a digital twin?
Well, okay, let me start. I was looking at Johnny, but let me start. So a digital twin, as I understand it, and actually I think there's, different communities have slightly different understandings, but how I would describe a digital twin is you have a physical asset or a physical system, and you want to create a digital clone of that. And I would say that a digital twin is where the two of them are somewhat in sync with one another. So there's information passing in both directions. So the two-way feedback, I would say, is important. So that if we're sensing something on the ground, then that information gets to our computer models, and it's able to update in a timely manner. I'm looking at Johnny and he's nodding his head, so I hope they haven't got that too wrong.
We had one podcast on another digital twin project at the Turing a long time ago, which was the 3D printed bridge project in Amsterdam. Yes. And if you go to Amsterdam now, somewhere in the city, you will find this slightly funky sort of modern looking bridge that doesn't look like any of the other canal bridges. And again, the idea is like, instead of just having a simulation that's completely detached from the real world objects, the real world object is covered in sensors and is, that's feeding back into the simulation. But I'm imagining that you're perhaps not able to cover the entire of Antarctica with quite so many sensors as this small bridge in Amsterdam. So,
yeah, absolutely. So Antarctica is huge. It's twice the size of Australia in size. So there's no way we're going to cover it in sensors. So we absolutely need to rely on, a whole suite of different sensors from satellite, understanding, the physics-based simulator models and feeding that into our digital twin. We have our ships and our autonomous vehicles, both underwater autonomous vehicles and over land. So all these different sensors need to come together if we are going to be able to say something about what the conditions are in Antarctica right now.
Nice. And is the high level aim of this project to sort of track, changes in like the overall, and I guess we're thinking about climate change here, what's going on in Antarctica, sea ice and other things?
So, there's 60 meters of sea level rise locked up in Antarctica in the ice. So if any of that was to melt, even a small fraction, we need to know about it. And, in order to do that, we need to have all these sensors. And we have radars, we have, the satellite observations that we mentioned earlier, but also we need to get to the ice and measure under the ice, and that's why we need to get our ships in there, underwater vehicles in there, and at that point you start to care about sea ice as well, because sea ice is already floating on the ice. It doesn't displace water, it doesn't contribute to sea level rise, but we need to understand a bit what's happening with the sea ice. It's important for conservation, for penguins, and we also very much work in the Arctic as well in the north, and so polar bears, the migration of caribou across the ice, hugely important. But to get to those ice shelves and the land ice, which is important for sea level rise, that's where we need to understand how the sea ice is changing and, how we get our ships in. And that's where sort of Johnny's work and expertise comes in as well.
Yeah, so it's really crucial that if you're actually monitoring Antarctica, you need to do it at a carbon reductive kind of idea. So you want to kind of do something, but at not the cost of climate change. So what we're looking at is we've got one project, which is route planning, which is, can we navigate this ship and give the most fuel efficient routes? But we have to understand how the conditions are changing. So it's this like constantly feedbacking loop, like a digital twin.
Yeah.
So we need to be able to say, this is what the environmental conditions look like. This is the route we should go. And in doing so, that kind of mitigates the effect of climate change. But then also on the broad scale outlook is to look at how can we replace a ship with another autonomous vehicle? Could we have gone and done a fraction of that science task with an autonomous vehicle and also gained a lot of insight, but at a lower carbon cost? So everything needs to come together and everything's interconnected in these complex digital twins.
I guess the route planning is almost like an Uber, right? You're trying to plan what's the best path. So besides the sheer size of Antarctica, which is already, I imagine, a big challenge, but what do you think are the main challenges to build these digital twins? What are the main things that have to be overcome to build a perfect digital twin?
I'll start by saying the infrastructure, the digital infrastructure. So let's step away from Antarctica for a moment. Let's imagine we're building a digital twin of a natural environment in the UK where we can put extra sensors there and we can, go there and take a temperature reading whenever we wanted. There's still a problem where we store that data, how we make it easily accessible for the community, how we feed it into models, and then you've got to think about how you can scale that up. So there's a huge underpinning digital infrastructure problem there. That's for, any digital twin of a natural environment or any digital twin. Then you take the challenge with Antarctica, which is often off, off the grid. We're not on the internet there or a lot of the time. You cannot get people there so readily. So suddenly it becomes a much bigger challenge. And that's, I think one of the biggest sort of challenges in terms of in the digital space. But then you've also got the sort of physical space of the physical challenge of getting them the ships. I mean, that's something we're also really trying to tackle now.
But you also have to think of things like puzzle pieces, because you could create one little bespoke section, but it needs to all put together into one global puzzle. So by pipelining and by defining an infrastructure where things tie together, you can actually get this sense of that immediately affects something that's already been generated. Another piece of software, another idea.
I mean, I'd also like to add, we're building a digital twin of Antarctica, and we're not doing that overnight. We're going to give ourselves 10 years. We need to take some weekends and holidays, and so we're not going to push ourselves too much. But when we built that, that needs to be able to glue together, a jigsaw piece with the digital twin of the oceans, because our systems are connected, and then the ocean digital twin would need to connect to our coastal infrastructure, and Turing's building a digital twin of ports, across the globe. Suddenly, all these digital twins need to connect together. So we need to be using the right standards. We need to make sure that we're using, we have the appropriate metadata, so the data on, what our data is trying to tell. So all this, we very much need to be building pieces that connect together. I often like to use the analogy. It's like, we all need to be working with Lego. Now, if some people are building things with Duplo and others with Lego, then suddenly they don't connect together. So we need to know from the beginning what our standards are, and that the interconnect, that the interfaces will be able to marry together.
So is some of the work you're doing now on developing such standards so that other research groups can, build interoperable digital twins that might be able to work with what you're doing?
Yeah, absolutely. So there's a project that has just finished with NERC, so the Natural Environmental Research Council, called the Information Management Framework for Environmental Digital Twins, IMFE. And the plan there was to sort of lay that groundwork so that you could build digital twins on top of that. So we're benefiting from all that good work for our Antarctic digital twin, but there are other centres across the UK that are building their digital twins using the same framework. And that should mean, hopefully, and there's some excellent people working on this, so I have faith that they'll connect together.
So from a layperson, someone who might be listening in the audience of the podcast, but what does this actually look like in practice? So I'm imagining with my data scientist brain that you've got lots of sort of input data, whether it's satellite data or other kinds of data, and you've got supercomputers and you're doing some kind of modeling and the data's feeding into that. But is there a sort of a way of explaining how that looks overall?
So each project is kind of different. So for our route planning one, we try and take in all these different environmental data sets and come up with a common grid or a common representation, which will then have how the ships or the autonomous vehicles respond in those conditions.
Right.
So if somebody comes in and says, we got a new autonomous vehicle, these are our designs, like battery levels, what it does, but it's highly affected by a new environmental factor, then you would have to input that new environmental factor into the problem. Right. But it all kind of ties together in a neat kind of pipeline. So it allows the user with these common data structures to actually tie in new data sets, tie in new digital twins, to actually have them building on top of each other.
And I think to add to that, I see a digital twin as a decision-making tool. So we can ask, what if this piece of ice broke off Antarctica in the next few months? What would happen to the rest of the land ice, and how that might accelerate, and how might that change our projections of global sea level rise? And therefore, should we be increasing the flood defences, that we've got around our low-lying lands and, the Thames Barrier, for instance. So suddenly it's that decision-making tool where you need that live updated digital version because the natural environment is always changing. We, with the surprises, we might see sudden changes we weren't expecting. And unless you have that live updated version, we might be caught off guard.
I guess the question is the plan overall to have in the future like a digital twin of the Earth, of the whole thing, right? I guess if you're all working in Lego, the plan is to then have this massive simulator, basically.
Lego Earth.
Yes.
So there's a lot of groups that are actually looking into this.
Yeah.
So, for example, ECMWF have DGE, NVIDIA have Digital Earth, I think it is. So all of these groups are kind of working in a silo and working from a commercial background. But if we can create a digital standard for all these digital twins, then we can start to tie them together as all of these research institutions, be them within the UK and external, can come together and actually work together on creating this digital twin of the Earth.
I mean, it's a massive ambition.
Yeah.
But one thing I like about the ambition is it drives some sort of common thinking and brings people together. So, for a long time, we've been doing digital research where we're all using different standards and we all have different models out there. So there's a lot of fragmentation. Now, suddenly this sort of very lofty, ambitious goal, in a way, is bringing people into focus and research teams into focus. So suddenly we are thinking about standards in the digital space. And I don't think we really did talk enough about the standards and how we build things that could glue together a few years ago.
It's great to see this in research, that there's a concerted effort to do this kind of thing, because obviously, there are many universities, there are many research institutes, and there's no particular reason, unless we decide that it's useful for everyone, for people to do things in the same way. I liked the analogy you gave earlier of it saying it's a decision-making tool, and thinking back to what you said, B, about how it kind of feels a bit like Uber, but for the Antarctic or the shipping lanes. I think that's a really nice analogy. I was thinking as well, companies like Google or Uber, I guess they kind of have what you could call a digital twin of a given city, and then you use their tool as to make a decision as to like what route you want to take. So I suppose it's kind of analogous to that, especially in the shipping context. Yeah. But then there's some much longer term decision making around what climate policies and stuff. In that case, let's say, what is it that you're going to hope to learn from the Antarctic digital twin that could influence what you then go on to do about the changes you're seeing?
So the digital twin and the sort of the benefits that could spin off this are multiple and huge. So I don't think there is just one answer, but decision making for shipping, for example, or conserving or protecting wildlife, the understanding and projecting future sea level rise. So there's multiple sort of benefits here. So in a way, it provides that sort of bedrock, tools that you could see lots of downstream benefits. So you may have a subgroup that will take the Antarctic digital twin that we're building, but they want to focus in one little area. And rather than having to build that infrastructure from scratch and get their own data sources, we've built all that pipeline for you. So that's the hope, that these digital twins that we're building of different subsystems of the planet, which hopefully will all come together to build a global, digital twin of the Earth. Massively ambitious, I realize, but that will really help create that common infrastructure, those digital tools that can all come together and help the wider community. So suddenly we're not duplicating effort, and every university group has to build their own pipeline because we've got that common infrastructure.
I have a question. Because we're talking about all of this decision making, but the things that actually could change and could help with the climate change and everything come from government bodies and policymakers, right? And I guess there's also some skepticism if you are showing them digital twin data rather than a prediction. How is it managed in this space between actually showing, look, this is a prediction, and how valuable the prediction is to people that don't do data science or science in that sense?
That's a really interesting question. So the way that we're approaching it at the moment is making it a support tool. So the way that you could say like Google Maps is in a car, you're looking at a route and you're saying, I'm going to take that one. It says it's lower in fuel. But then once you've started driving the route, it's not saying immediately turn slightly to the left. It's just giving you the broad route to take. So that's adding a support to the problem. So a mariner, so a captain on a ship, can look at this and say, this is what I'm going to do. It's slightly different to your route, but there was a reason why I picked that. So then that removes this kind of risk and liability away from it. But in the long run, what we're also doing is AI task planning. So that's looking at how we position different science tasks. And this isn't for a mariner or a ship operator. This is for someone looking at the carbon cost. Somebody in an accounting office that can say, this is the amount of science we did with this much fuel this year. Should we reduce the fuel down because it won't make too much change to the science. Or equally, it could be, should we do stuff differently to then reduce the carbon cost? So it depends on your audience of how you kind of position these different tool sets.
And Ed, going back to your question earlier, like how people might see or interact or understand a digital twin, you can also imagine dashboards which will be live, updated with the information that you need, and not providing too much information because you can drown people with information. But a policymaker should have a dashboard with just the information that they require. So when they are in the boardroom, let's say, or businesses, but there's a meeting where big decisions need to be made. They need that information at their fingertips. And rather than, I think what probably happens now is the boardroom comes up with a question and then someone has to go away for 3 months and work it up and, do the analysis. So we need that instantaneous, information, at your fingertips using a dashboard. Now, it may be that using the AI, which we use, bring AI into digital twins, that may not be the absolute best answer you can get. You would still want to run your climate model or your ice sheet model, but it may be good enough. Sometimes you don't need the best answer. You just want to know, is it important enough? Is it something I should be worried about? If the AI says, you know what, this is minor, you've got much bigger challenges here, then that can really help the discussion and the decision making. So it's about what is good enough for decision making. And I think that's also another way to look at it. Quite often as scientists, we try to get the absolute best information out there, but not necessarily in a timely manner that's needed for policy making.
That's really interesting. There's those. You've identified those sort of two different ways of doing things. One would be the sort of traditional, let's answer the question, the scientific research question to the best possible degree. The other, like, what's a practical tool that can be, live used? And I think it's kind of interesting because a lot of what we consider now to be called AI, quotation marks, whether we call it whether it's predictive modeling or digital twin or whatever it is, but it feels like that's the direction it's going, right? It's people might have said a few years ago, AI taking our jobs, but increasingly it seems to be AI assisting us in our decision making and jobs, and that actually it's only as useful as the expert using it, because they're probably the people who have helped design it in the first place.
Yeah, I mean, on that, I often use the sort of slogan, if you like, the AI can help scientists do science. That's what we were trained to do as scientists, and too often we're spending over half our time cleaning up data, moving data from this drive to this drive, changing the format, relabeling things, and that's not why I became a scientist. I don't get out of bed every morning to think I want to format some data. So I think if the AI can really help with the mundane stuff, as scientists, but also in everyday life as well, then that can only be a good thing. We can then, use our training. I'm a climate scientist by training. I would like to be able to spend more of my time actually tackling some of those chunky climate problems. So absolutely, there is a fear right there that AI be taking our jobs, but actually I think there's what the reality is, at least I'm seeing, is that AI, at least in my field, and I cannot speak more broadly, but AI can make our work more enjoyable and fun, and focusing on the things that we've been trained for.
I think that's really cool. Yeah, I think that's an empowering in this sense, right? It empowers the scientists to spend more time doing other things, which leads me to the next question, because you briefly mentioned, and we had like a bit of like a spoiler or about something called IceNet, and so I wanted you to, if you could at least explain a little bit, and maybe other projects that you're working on.
And I should say as well, like, although we've just talked about AI being used to help us do science, I think this is probably an example of where the AI is the science.
Yeah. Okay, I can say something about IceNet. So IceNet is one of our projects that spans the British Antarctic Survey and the Alan Turing Institute, and it's essentially an AI algorithm that can forecast changes in sea ice and producing maps of sea ice up to a few months ahead. Now, we built this and we tested it against the current best sort of traditional way of doing things, the traditional physics-based models, and it outperformed those predictions. So when I say outperformed, we compared our AI model against what actually happened, using satellite observations versus a physics-based model, a traditional model, and the AI was able to do a better job. They had higher accuracy. Now the IceNet algorithm, and we've this is one of our core tools, if you like, AI tools in our group, because it's so important for the ship navigation work. It's so important for the task planning that Johnny has mentioned in terms of what tasks should we do in what order to reduce our carbon. But then also we're using it for understanding how wildlife will migrate across the Arctic, and also being able to anticipate when they might be in danger. So if there's going to be a low sea ice year coming up, or if the next few months we're going to see a massive reduction in sea ice, we can actually provide that information to conservation experts to say, actually, there's a risk here that this herd of caribou, I don't know if they're called a herd, but this group of wandering caribou potentially could be at risk, and we may see mass drownings. Can we do something and get ahead of that? So suddenly IceNet has this massive, again, a bit like our digital twins earlier. It's one of these sort of tools that we're using as a bedrock for lots of other downstream tools. So it's fantastic that it's doing such a good job. It's also, now the IceNet model is trained, you can run it on your laptop. So in real time, we can get, very quickly, we can get answers to those what if questions, like we were saying earlier. So what if sea ice in this region does suddenly reduce? What's the knock-on effects of that? And that's where you start getting again into your digital twin, that you can ask those questions in real time. The traditional methods, you would have to ask a specialist to go away and rerun their climate simulations and get new data, and that can take quite a while. So I think AI really does empower that decision making process.
So what is it exactly that sort of makes it so I understand that the previous models were sort of physics based, and presumably that involved programming the laws of physics as we know them. And this is obviously using machine learning, but it's interesting that you're saying that a second part of that is that it's easier to use as a sort of user than those simulations might be.
Yeah, I mean, once that model is trained, then it's at your fingertips. You can click a button and run it again. One thing I didn't say is we've trained this model on all the historical data that we can get our hands of. And one thing that's really great with AI is that it's far more flexible. You can bring lots of different types of data sets together. So fragmented data where, there may be some temporal or spatial gap in our data sets. And we can blend different data sets together, including the outputs of future climate simulations. So one of the challenges in forecasting is that we are ever pushing ourselves towards, a warmer climate. So you could think that our forecasts are constantly being tested in, uncharted territory. So one thing we did with IceNet as well is show it those possible future scenarios by bringing in climate model runs as well. So again, that was a really novel aspect of our algorithm, which you don't necessarily see in those traditional physics-based approaches.
Okay, so that's interesting, because your physics-based approaches, is that because it's it's not learning from the past data, whereas the machine learning is learning from you can somehow include the fact that there's a global trend to warmer, as well as just, well, here's the laws of physics as we understand it, and this seems to be what happens.
I mean, absolutely. I mean, I would say that the people coding these simulators, these physics-based models, are learning from the past. So, they've seen what's happened in the past, and they're, using their expertise to build these, and they do an amazing job. But the machine learning approach can directly learn from that historical data. So that's, again, can really speed up how you ingest new data as it comes online. If there's a new satellite that's suddenly in orbit, how we bring that into our AI, it can really be.
I guess without having to hard code every single thing, which would be the biggest difference, I would say.
Exactly.
Yeah.
I can imagine if you're switching to a new data source as well, that doing things before the machine learning approach would have been very difficult, because it might have been, you'd have to redo everything from scratch, perhaps. Yeah. Cool. So one of the other projects that sort of we touched on a bit earlier is the automated route planning. I wonder if there's anything more you can tell us about the, in particular, the Sir David Attenborough.
Yeah. So at the moment, we're looking at integration with the ship directly. So what I mean by this is to have a system that they can actually run it on the ship, get back routes that are lowest carbon, quickest route between a start and end waypoint. And then that will allow the navigator, the captain, or the first mates to actually say, we should take this route. It's going to save us this much fuel. But with their expertise that they know how the conditions could affect the ship. But we're leveraging all the work that IceNet's been doing. So using the sea ice forecast into these navigational routes. So we can say, don't go now to this location. There's a huge sea ice effect. Wait a little bit of time and then go. And you could save a huge amount of fuel.
And is the ship itself, is it fitted with lots of sensors and stuff?
So the ship's got tons of instrumentation on it by different companies and organizations. But what we are also looking at is how the fuel usage ties to environmental impacts. So looking at data streams off the ships and saying wind is affecting the ship this much, and this is what you would expect the fuel to be. So this is kind of pulling together this digital twin idea where we'll start to get a more deep and rich knowledge of how the ship responds with the fuel usage.
So I wanted to add something, and I realized when we talk about AI and digital twin, it feels like we're moving towards this completely autonomous world where we don't need people. And actually that's not what we envisage in our digital twin. We very much need humans, expertise to be there. So we call it, human in the loop, that a digital twin might be a decision-making tool, but that decision should be taken by a human, which is why you need, the shipmasters, the first mates to be there to use that information and to say, I'm not going to, that doesn't work for me. I don't trust that. I'm going to take this other, I'm going to use my own expertise and judgment. But we also need to get that feedback from the human. So, by having a human in the loop, they might say, you've done something wrong there. We need to know about that so the machine learning can improve for next time. And that's where it isn't an either or. I think absolutely it's a decision-making tool and a support framework.
This is an interesting point because the decision maker has so much knowledge of how the environment unfolds, but they can't visualize these really complex 3D environments. So how the sea ice would change. They don't have that knowledge so much, but they do know how to navigate through them. So by generating a toolkit which is grounded on how they think about these things, it becomes very useful for them because they don't have to think about, is the sea ice going to move here with this uncertainty? That's really difficult for humans to do. But they can say, well, if it does move there, we'll go this way instead.
And we're talking about all of these sensors and all of this, measuring things in Antarctica, but how much does the presence of the sensors change the environment around them, right? Because Antarctica doesn't have things. So if you certainly have a ship going through, that we assume it's going to change as well a little bit of the own environment around it, right? So how is this mitigated?
So there is an environmental impact from polar operations, but what we can do, and we start to give to them with these route navigation toolkits, is you can put in areas that are of ecological sensitivity. So normally they kind of skirt away from these regions, but you could actually put that in the route planning. So it could be, don't go here, there's penguin colony here that would be affected. But in the long run, what we can do is actually tie everything back, as Scott mentioned earlier. So is navigation in these areas affecting the climate in such a way? How does this have a feedback? And this is really important for, could be ecotourism around Antarctica, could be fishing. All these things play a role on the climate change. So we do have to understand them.
Yeah, I mean, it's interesting to think one of the maybe small benefits of climate change might be that in the polar regions there is more, opportunity for shipping and for tourism, as you said. But then obviously you wouldn't want that to be sort of self-reinforcing in that increase makes the climate change even worse. So it's good to see that these things are being thought of even at this stage.
Yeah.
So maybe we'll begin to wrap up, and I wonder if the two of you have any sort of more general thoughts on thinking about both climate change and AI. I think both are things that people are worried about for slightly different reasons, maybe. But do you think we're moving forward to a world where AI is going to save us from climate change?
Interesting question. The pace of climate change is, accelerating, and we've seen increasing weather events year on year. And at the same time, we have, this acceleration in AI capability as well. So it's I see a lot of, I think it does make sense for us to be using the power of AI and that acceleration for good. And if we can understand our changing climate, how we might mitigate against effects, if we can predict, let's say, storms, better accuracy at longer lead times, then that should be able to, help our communities, optimize our energy networks or agriculture. There's a lot of benefits that can come from improving our prediction.
Just to add on that, it's really important to do operations and actually sample these areas to understand the prediction of climate change. So anything that we can do to actually minimize the carbon usage, but still maintain that fidelity and that resolution is imperative.
Yeah, exactly. I mean, that's a real, something we just got to keep an eye on, where we want to keep understanding our world and monitoring it, but we need to do that, in a carbon neutral way. So using new satellite sensors as they come online with increased resolution, we need to be using those more and more, but, keeping the detail that we've had for years. And long-term measurements are so important, but we need to make sure that we are actually using them. If we've got long-term measurements and we cannot use them in some way, they're not providing the detail that we need, then, and there are other methods out there, then we do have to ask our question, what's the best way to capture the measurements we need?
It's an interesting point as well about, carbon sort of emissions minimization. I think most people, when they're thinking of things like route planning, we're thinking about getting from A to B faster. And so the goal there is just, time saving. But of course, if you think about the way the world works, and whether it's shipping, whether it's, lorries or cars or anything, if you can make their journeys more efficient, then of course that's going to result in fewer emissions. So it's really interesting to see that the same kind of technology, which you might think is, primarily about just making our lives more convenient or making it better for business, but it's also, of course, having this big effects on climate itself. So hopefully more of that.
Well, thank you so much for joining us. I guess the last thing is to ask is for you to tell our listeners where they can find you. So social media or websites or something.
Yeah. So I am Scott Hosking, one word, on Twitter or X or whatever it's called these days, and GitHub. You can find our BAS website, bas.ac.uk/AI. We've got a nice alias there, makes things simple. And then if you go to the Turing website and search for research in environment and sustainability, a lot of our activities are on that site.
Yeah, so the BAS website is a fantastic place to go. It's got all of the information for the AI lab, but it's also got the projects that we're doing as well. So you can find more about us there, as well as the different projects we work on.
Maybe a good final question to ask for anyone interested who's listening, and you don't have to necessarily be your own organization, but do you think this sort of field of AI for climate science is a good one to get into? Are there jobs? Are there, what's the field looking like at the moment?
Yeah, it's accelerating, not just in the academics, community, but industry as well has to take seriously the climate impacts. Also, just to maintain business into the future, we need to be aware of how climate's going to change, what that's going to do to our systems, agriculture, energy networks. There's cost implications here as well. So all industries are now starting to care about climate, and so that has knock-on effect in terms of jobs and what level of detail and knowledge we need.
Awesome. So if you're interested, get involved. All right, Scott and Johnny, thanks very much.
Thank you.
Thank you.
Thanks for listening to this week's episode. The show is hosted by me, B. Costa Gomes, Ed Calstry, Joe Dungate, Christina Last, and Anika York. And the episodes are produced by Luca Lane. Music for this podcast is produced by Jam and Sun. You can listen and follow via the link in the description or by searching Jam and Sun on Instagram.